Okay. Honorable Mr. Adrián Nombre, my fellow young professionals, ladies and gentlemen, good morning, good afternoon, and good evening. It's my great pleasure to welcome all of you to today's ICOLD YPF webinar on sustainable water resource management under changed climates. My name is Yang, board member of ICOLD YPF. This webinar is convened by CFBR, Code, and ICOLD YPF. We firmly believe in the power of collaboration and knowledge sharing. Our forum serves as a platform for young professionals from across the globe to exchange ideas, share experiences, and contribute to the sustainable development of hydropower and dams. We aim to provide a supportive network that nurtures the growth and development of young talents in our industry. We recognize that tackling the complex challenges faced by the dam and hydropower sector requires diverse perspectives and innovative solutions. It is through initiatives like this webinar that we are able to bring together a diverse range of experts, young professionals, and industry leaders to exchange knowledge, inspire creativity, and drive progress. During the webinars, we delve into various facets of dam and hydropower industry, discussing topics such as technological advancements, environmental stewardship, social compact, and project management. It shows it just started. Oh, okay. Through insightful presentations and discussions, we hope to generate new ideas, foster collaboration, and inspire a collective vision for a sustainable and a prosperous future. Today, joining me as a co-moderator for this insightful session is Mr. Julien Hussein from France, the youth group coordinator of CFBR, who has made great efforts in the preparation for this webinar. Thank you, Julien. We are delighted to have all of you today to discuss the critical topic of water resource management in the face of evolving climates. Before we proceed with the presentations, I would like to extend a warm welcome to our distinguished guest, Mr. Adrián Nombre, the Honorary President of ICOLD and Chairman of ICOLD TC on capacity building and dams. Thank you, Mr. Nombre. We are honored to have you with us today, and we're eager anticipating your opening remarks. And I would like to welcome our four excellent speakers who will make presentations. They are Mr. Evangelos RABIAS from Greece, the Business Development Manager of Hydroplus, Dr. Jiabo YIN from China, Associate Professor at Wuhan University and the University of Oxford, and Dr. Adrián Morales Torres from Spain, the Partner and Technical Director of iPRESAS, and Mr. Ronny ROSILLETTE from France, the Head of Irrigation Water Operational Office at Martinique Collectivity. It is worth mentioning that Ronny won the ICOLD Young Professional Award of 2022 in Marseille, and Adrián won the prize of this year in Gothenburg. After their enriching presentations, we open the floor for discussions alongside with the pre-submitted questions from our registered participants. We also encourage all online attendees to ask their questions following the presentations. Our speakers will be delighted to address these queries and offer their expert perspectives. Now let's commence with the first part of today's webinar. I would like to invite Mr. Amada Nombre to deliver his opening remarks, setting the stage for our engaging discussions on sustainable water resource management under changing climates. Mr. Nombre, please take the floor.
Thank you, Mr. Yangan. It's a very pleasure for me to take part of this important webinar organized by the young engineer professional.
Hello? Oui, ça va et toi? Oui, je suis en ligne. D'accord.
Mr. Nombre, it seems we don't hear you anymore. Seems we have some trouble, like internet connection problem with Mr. Nombre. Your screen is freezing on this side, and I cannot
Mr.
really hear
Nombre,
you.
can you hear us?
I have some difficulty to share my PowerPoint. I propose this. Are you understanding me?
Mr. Nombre, can you make your
Mr. Nombre,
speaker
we hear
louder?
you a little bit faint. Yeah, if you can speak a little bit louder, please.
Do you hear?
Are you going to share your slides now or later?
I'm trying to do it, but I have some. Okay, I propose to continue my speech.
Okay, a little bit better now.
So I am grateful to the young professional engineer, to Chincourt Committee of Friends, those who have organized this webinar, providing the opportunity to discuss the important topic of the world today. Climate change is a reality and present threat for human being and its environment. You have the global warming, the food consequences, and the glacier, and the level of the sea, water. You have water scarcity. You have also extreme floods leading to flooding of cities and also creating the man-made infrastructure and natural hazard like tsunamis. This is happening in all the world and in all the region, different regions. Warming change will vary in different regions, potential include increased flooding and drought, water quality impairment, and salt water intrusion to coastal water supply. All the water cycles are impacted by the global climate change, and all the regional I was saying. One of the facts I want to point out is the complexity of the global climate change. It is very important because to know that we know a lot of things about climate change, but the unknown are very, very important and leading to for professionals and scientists to continue working good. The main objective for us, water management, to ensure clean water, food, cheap and massive clean energy, food, settlement against floods and drought, power, proper navigation for good and person transportation. I'm sorry the slides are not present, the possibility to be presented. In our knowledge today, we have the area of certainty, we have the knowledge universe, which includes the area of certainty and the uncertainty zone, and we have an unknown universe to keep in mind, which is also extremely important. Today we have a challenge to feed an increasing population, to ensure water as a clean water for a population which is increasing. We are the present situation with billions of people lacking electricity, clean water, sanitation, but this population is increasing. So at the total, we have to triple the food production, we have to triple energy production, we have to use less carbon in this production, and we need to address these issues. Awareness of the need of integrated management of water resources in the context of global climate change is a common concern today for the international community, including our association, ICOLD, ICID, ISA, and other organizations. We need to work at 3 levels: to protect water, to protect human being against water, and to protect water. To address the thinking, we need to think from rain drip to large basin development, developing multiple infrastructure and network thinking. International collaboration is needed to make these progresses. The need for the young engineers to be involved in this process because it is their world, it is their future. But as young engineers, we should not overemphasize modern tools of calculation that are necessary for our profession, but we should keep in our mind what I was presenting at the start of this presentation. It is the certainty universe, the uncertainty universe, and the unknown universe. We should keep in mind this notion. The fundamental role of a political decision maker with short deadlines and value such as maximum profit, which is not in adequacy with a scale of thinking, the scale of addressing the global climate change. And we see at the international level the difficulty to achieve agreement, even we have progress at the international level. Climate change is one of the challenging situations associated with engineering based on the limitation of knowledge. We need to be careful and consider the best of our knowledge to manage water accordingly and improving our work as far as our universe of knowledge enlarging. Humanity is growing, the needs are diversifying in terms of quality and quantity. The natural hazards are being more and more larger and unpredictable. The role of research and development in these conditions is very important, and I am sure that young engineers are very interested in this area. The main role of water storage for climate change mitigation. According with the data, a reservoir created by human and natural lakes represent 31% of the global renewable water. This is to say that dams, reservoirs will continue to play a vital role. And as Mr. Lampere used to say, we have a dam of our fathers and mothers. Now we need to have a dam of a century coming. So it is a huge challenge for innovation, for imagination, and we see that we are progressing. Yes. I take the example of renewable energy. Solutions are coming, and we need to think globally. We need to extend cooperation. We need to extend understanding between people to get the best result of our process. And to give some data according to the IEA annual report for 2022. Hydroelectric production between 3,449 and terawatt between 2010 and 2021. This represents 15% of the global electricity production. Hydropower represents more than 80% of the renewable energy generation and prevents emission. Hydro generation prevents the use of wood fuel in less developed countries and reduce the rate of afforestation and CO2 emission. And in the context today, we are seeing a lot of progress. Floating photovoltaic panel, which is being important in the area of energy. We have also the development of PSP, not for energy only, but to store water for the different use. And now to end my presentation, I will talk about the cooperation between ICOLD, ICID, IHA, World Commission on Water, who had made a lot of progress. If I take the example of the clean water, the access to clean water has been recognized and decided by United Nations as a fundamental right, and it's important for our ethics for the future also in working with climate change domain. And ICOLD also is working hard to contribute by publishing bulletin on dams and environment, by reinforcing the capacity building for the young engineers, but also for engineers coming from less developed countries. If I take the example of IHA, we have the IHA protocol for hydropower, which is taking an important part of the global climate change, and the United Nations, the JIN, are working hard to increase our knowledge, to reduce uncertainty in the universe of our knowledge. So I am sure that this webinar will put at a stone in our general work, in our activity, task, to improve and to connect and bridge the young generation. Thank you very much. Good symposium. All my apologize for the difficulty to share the slide at the beginning, and I am very sorry. Thank you very much.
Thank you, Mr. Nombre, for your inspiring words and valuable insights. Your presence today truly elevates the significance of our discussions. Now, I would like to hand over the proceedings to my co-moderator, Mr. Julian Hosing, who will guide us through the series of presentations by our expert speakers and also the discussion part. Julian, over to you.
Thank you. Today we have a dynamic lineup of experts who are addressing climate change challenges. And guess what? You are not just a spectator. You can also use the chat to dive into the conversation and ask your questions there. So today we have first Mr. RABIAS, who will unveil innovative approach to dam rehabilitation. Then Dr. YIN will then take us through his groundbreaking research on extreme storms. Dr. Morales will delve deep into the intricacies of risk assessment. And last but not least, Mr. ROSILLETTE will explore the shared water usage of a beautiful Martinique island. Over to you, Evangelos.
Hi, Julien. Hi, everyone. Thanks for the invitation. I'm happy to be here in this nice event. Let me share my screen and we can start. I'm pretty sure I will be faster than the 15 minutes, so we have more time for the questions maybe at the end. Let me know if my screen is visible. Hope it is. Okay, perfect. So I would like to present you a rehabilitation of Sans Souci Dam, a project that was completed in the island of Mauritius last year. To start with a little bit about the project, the island of Mauritius is located southeast of Madagascar in the Indian Ocean. The dam is located in the middle of the island, where there are several dams in the middle of the island of Mauritius. You can see it here on the map. It is a rock-filled dam with a clay core. This is the dam here, if you can see my pointer. And it has a WES crested weir as a spillway, which continues with a chute, a concrete chute that ends in a flip bucket at the end. The main purpose of the dam is hydropower, and the power plant is located downstream and has 2 Francis turbines, 15 megawatt each. The main characteristics of the dam, you can see them here on in this table. There's no reason now to go over them. You can find it, read it after in the presentation. Here we have a nice picture, a nice photo of the dam. You can see the embankment is here. This is after completion. The spillway with the fuse gates, the spillway chute. This is the intake tower for the power station. And the power station is located downstream. It's a couple of kilometers, so you cannot see here the reservoir. And as you can see, all the landscape, it's very, very beautiful. The objective of the project, the objective was installation of fuse gates on the spillway crest in order to increase the reservoir capacity by 3 meters, which results in an increase of the storage by 1.36 million cubic meters, which also results in an increase of the power generation from 3 gigawatt hours to 10 gigawatt hours per year. It's not a huge number in general, but for Mauritius, for the island of Mauritius, it's significant. So the benefit, what were the benefits? More water available, more clean energy from 3 to 10 gigawatt hours per year, a boost in the hydro capacity of the power station due to the increase of the head of the turbines by 3 meters. And this enabled the reduction of the existing thermal energy production, because they have some thermal power plants, and a further reduction of the CO2 emissions by 1,800 tons. The design and the works had the total duration of 12 months. Design was approximately 4 to 5 months, and the rest 6, 7 months were the works. During the works, we had to develop several methodologies to adapt to the technicities of the project. Of course, highest safety and quality standards were enforced. During the works, we had to successfully respond to 3 flood events. They were not minor. They were maybe 10 to 50 years old, 50 years flood. And also during the, we had the COVID restrictions, and we managed to complete the project 1 month in advance. To talk a little bit about the technical solution, which is the actual innovative element of this presentation, it's the fuse gate system. Fuse gates are freestanding blocks, you can see them here, made of concrete or steel. In this project, we had a structure, a base, you can see here in the 3D model, that was made from steel, and it was retrofitted in order to match exactly the shape, the curved shape of the spillway. And then we cast in place the concrete walls, and at the end, the well, which is always from steel. So we're talking about freestanding elements. They are set on the spillway weir, set, not fixed. We don't fix them. You just pick them up and you set them. There's nothing fixed on the spillway. Put them one by one, side by side, and they create a watertight barrier which enables water to be stored from the initial spillway crest, which is here, to the new, or here if you want better, to the new fuse gates crest, which is here. So all this height is the additional increase in the storage capacity. For this project, we had 14 units, all these are 14, 3.64 meters high, and the shape was labyrinth. How does it work? For all the normal conditions, water is stored behind the fuse gates. So this is the extra capacity. When we have the normal flood events, water is able to overflow above the fuse gate crest, just like a normal labyrinth spillway. At the conditions that we have exceptional floods, let's say the 100 years flood, the 500 or the 1000 years flood or above, water will start overflow over the fuse gate crest, and the reservoir level will start to rise. At some point, it will reach a predetermined elevation, which we design and set during the design phase, and water will start to reach the elevation of the entrance point of the inlet well. So as soon as the water starts reaching here, it will enter to the well, and this well has direct access to the bottom of the fuse gate, which is a hollow, which is a chamber that is empty. Water will start to fill up. It will create an uplift pressure, and this uplift pressure will create the triggering mechanism for the fuse gate to be flushed away. How is it flushed? The only thing that is fixed on the spillway is this small black box that you see here. It's called two abutment, and this creates the rotation point for the tipping and also prevents the fuse gates from sliding, because as I said, all this element is not fixed. It's just set on the spillway weir. The tipping of the fuse gates, the flushing, is not happening all units at the same time. It happens one by one, and this is controlled by the predetermined elevations of the inlet wells. We set the inlet wells at different elevations, so water will enter here at different elevations. And these elevations, during the design phase, we calculate them and we know at which flood they will occur. So normally, for this project, the first tipping happens for the, I think, 200 years flood, if I'm not mistaken. Before that, before the 200 years flood, all the fuse gates will stay in place. During the design, we developed a CFD model in order to check the hydraulic characteristics of the fuse gates and of the spillway all around. The works, first phase of the works was the clay core rising. This is not usually necessary, but in this project, the dam owner, they wanted to do it. So what we did is we raised the clay core until to reach the new full supply level. You can see it here. The excavation works for the clay core rising in these two photos. Second step was the spillway preparation. We're talking about these minor works, which you can see in this photo here and here. And this is actually the two abutments, the small black box I showed you in the picture below. This is the only thing that we fixed on the spillway weir. Next stage is the steel base. The steel base was fabricated, manufactured, and transported on site. Because of the size of the base, because we're talking about 6.6 meters in this dimension, and if I recall, around 4 point something in this direction, it was assembled on site. Then with a mobile crane, lifted and set on the spillway weir. As you can see here, it's retrofitted in order to fit exactly the profile of the curve of the spillway. So we set it on the spillway crest, and then on top, cast on site the concrete walls, 2 vertical walls and 1 inclined. And at the end is the installation of the wells, you can see here, and of the water tightness system, which is actually what a system that enables enables water tightness in between the elements. Some photos from the construction, the concreting, the base, concreting, the start of the concreting of the base and the walls. This is how it looked like during, after the completion of some elements, and this is during the construction of the walls. To summarize the benefits, the dam was optimized with a cost-effective solution in less than a year. Water storage, sustainable development of water storage infrastructure, optimization of flood management. The overall safety of the dam was enhanced to protect people and properties, and all that without changing the initial characteristics of the dam. Maximum water level stayed the same. All the initial stability design stayed the same. Nothing was changed. The reservoir capacity was increased. 31% was for the dam. More water available, more energy available from 3 to 10 gigawatt hours per year. A boost in the hydro capacity. A reduction of the thermal energy generation, and a further reduction of the CO2 emissions. On the photo on the right, this is a flood event that occurred, I think 2 weeks after the completion of the project. We had the flood event, so it was tested from right at the beginning. And this is how it works when you have the normal floods. Water goes up to here and flows like a normal labyrinth spillway. A few photographs after the completion area. This is the spillway with the fuse gates, upstream to downstream. Now you can see better. Also, you can see the chute and the flip bucket at the end. Again, from the top, And here's a picture with all the reservoir. Our references. And thank you very much for your attention.
Thank you, Evangelos. Your insight into the Sans Souci dam were truly enlightening. Transitioning from dams to floods, we are honored to introduce Dr. Jiabo YIN next. And as an esteemed associate professor at the Wuhan University, Dr. YIN research spans a wide spectrum of earth science, particularly in the context of climate change, is a forefront of exploring the multi-scale nature of the continental hydrologic and carbon cycle. Without further ado, please welcome Dr. Jiabo YIN.
Okay, thank you. So can you see my screen? Okay,
Yes, we can.
That's good. Thank you for joining this online conference. Today, I'm happy to present a brief introduction about my recent work. The topic is, does the whole structure constrain future precipitation extremes and flooding? The figure to the left shows the beautiful coral reefs. You can see the coral reefs are very beautiful, but a recent Nature publication asserted that if we didn't take action to mitigate the global warming, all its beautiful coral reefs will disappear by end of the 21st century. The figure to the right shows the Australian wildfire. You know, this wildfire has killed 500 million animals and plants. Due to these events, more attention has been paid to global climate warming. As a young scientist in hydrology, I would like to know the underlying physical mechanism behind the hydrological extreme. For example, during recent decades, we observe that more frequent and more intensified hydrological extreme, such as precipitation extreme, flooding, droughts, heat wave, and the wildfire events. Okay, due to the time limitation today, I will show you some brief example about our study on hydrological extreme. According to the Clausius-Clapeyron relationship, it's just a physical foundation. We can look at the red curve. You know, according to the Clausius-Clapeyron relationship, the atmospheric water vapor holding capacity should increase with temperature rising. You know, the water vapor is the physical basis for precipitation extreme. And from the physicals, we know that the saturation water pressure will increase with temperature rising. So many people think that the precipitation extreme will also increase with temperature rising. However, by using climate simulation and observation, we find that in many regions, the temperature is rising. For example, in Western United States, temperature is rising, while the precipitation here are declining. So the results suggest us that, unlike the physical expectation, the precipitation and the temperature relationship are more complicated than our traditional expectation. Particularly, we have reported a whole structure between precipitation extreme and the temperature. So you may raise the question, what is the whole structure? Okay, we can just look at the red curve. The precipitation extreme will increase with temperature rising, but when the environment is very hot, we can observe a decline branch. So we call the red curve as a whole structure and define this point as the peak point temperature. This is just the results at a global scale. We have detected the relationship between precipitation in extreme and the temperature. The red color indicates monotonic increasing relationship. So the red color is widely impacted by the international climate community. However, in most regions across the globe, we can observe it show a peak point temperature. A peak point temperature just shows that it shows a hook structure. So, at most areas of the globe, the precipitation didn't increase with temperature rising, but it shows a hook structure. However, the underlying causes of this widely reported hook structure is still uncertain. So our study is trying to understand the underlying physical mechanism behind the hook structure. First, we just show you some example of the hook structure. For example, in region 1, it's a hook structure, right? And in region 2, it's also a hook structure. And this is similar in region 3. However, we find that the hook structure have different shapes. For example, in region 1, the turnaround point is about 10 Celsius degrees, while in region 2 and then region 3, the turnaround point is about 26 Celsius degrees. So we will find that the hook structure is more complicated. That's why we should try to understand this hook structure. First, we just try to understand the relative humidity and the energy transport during precipitation extreme. You know, during the precipitation extreme, both water vapor and the energy transport are very important. So first, we can try to understand the water vapor and the energy transport in the precipitation extreme. Because I know so many people in this online conference may have little background in our hydrology. So maybe I will show you some simple example, okay? For example, in the Western United States, the precipitation extreme is declining. And we find that in the same region, the relative humidity during precipitation extreme is also declining. Even though the K, it means the energy for precipitation convection is positive. So the results suggest us that maybe the hook structure can be attributed to the water vapor availability. So we can try to pay more attention on the water vapor availability. For example, in Basin 1, Basin 2, Basin 3, these are catchments in China. We find that when the environment is very hot, the relative humidity is also declining in Basin 1, Basin 2, and Basin 3. And in these 3 basins, we also observe a hook structure. But this is different in Basin 4. You can see in Basin 4, the relative humidity do not decline in a hot environment. And it's interesting to find that in the Basin 4, we didn't notice a hook structure. All the results suggest us that the continent most limitation due to atmospheric dynamics may constrain precipitation intensification. So we can attribute the hook structure to the continent most limitation, and the continent most limitation is caused by the atmospheric dynamic. Now we raise a new question. Both atmospheric dynamic and atmospheric thermodynamic have a great impact on the hook structure. how to understand their potential impacts is very important. So we employ a physical-based diagnostic model to quantify the thermodynamic and dynamic contribution of precipitation extreme. The physical-based diagnostic model is an energy-based balance model. It can simulate both the local vertical motion and the available atmospheric moisture in the atmosphere. You know, in the atmosphere, in a precipitation event, we need water vapor, and the water vapor need to increase in the atmosphere, and then the precipitation can be generated. So we can constrain this physical-based model to simulate the precipitation extreme event in the atmosphere, and then by formulation derivation, we have derived the formula to partition precipitation extreme into a thermodynamic component and a dynamic component. Okay, I know the physical mechanism may be somehow complicated, so I will try to show you the physical mechanism by using the simple plot. Okay, the red curve is just a hood structure, and here is the peak point temperature. By using our physical model, we find that the atmospheric thermodynamic always contribute to precipitation extreme, so it's a monotonic increasing curve. But this is different for the dynamic component. We can see when the environment is not hot, the dynamic contribute to precipitation increase. But when the environment is very hot, the dynamic will show a negative contribution to precipitation. So we can try to partition the effects of atmospheric thermodynamic and dynamic impacts on precipitation extreme. That will raise a new question, because the total impacts of atmospheric thermodynamic contribute to precipitation intensification, while the atmospheric dynamic decline precipitation in host environment. So for a long time, people usually pay more attention to the atmospheric dynamic, because the atmospheric dynamic is dynamic. It's changed over time, and it change under climate change. This attention has been paid to the thermodynamic. But we raise a new question: do all the thermodynamic components always intensify precipitation extreme? This is our recent conceiving new scientific question. We can try to answer this question. Okay, I will not show you the mathematics and the formula. I know maybe this is somehow complicated. We just by further decomposing the most adiabatic derivative of saturation specific humidity, and then we partition the thermodynamic component into pressure component, a temperature component, as well as a left rate component. Before using our physical model, we need to confirm the performance of our physical model, right? Okay, the figure to the left just show the observation, and then the figure to the right just show our physical model simulation. We find that at the same time stage, the two figures are similar. So the results suggest that our physical model have a good performance in precipitation simulation. After confirming the performance of our physical model, we can run the model to answer our scientific question. And finally, we find that the thermodynamic component do not always contribute to precipitation intensification, because the temperature lapse rate will also change under climate warming. So we can try to use big data such as satellite, real analysis, observation, and the physical model to answer the question related to a host structure, and we can attribute the host structure to water vapor availability. Let's go to our last topic in today's conference. We know the host structure has not been reported by many studies, but people usually want to know, does the host structure imply a potential upper bound for future extreme? To answer this question, we need to project future hydrological extreme. For example, we need to predict future precipitation extreme and the future flooding. Traditional study usually use the hydrological model to project future hydrological extreme, but the traditional hydrological model cannot simulate human activity impacts. To solve this question, we can try to propose a hybrid hydrological model and deep learning combining model. Our hybrid model can not only capture the physical process, but also consider human activity. This just shows the results. We find that by using our hybrid model with combination of physical model and the deep learning model, the hydrological simulation performance can be improved. This is just a case study in China. We can also try to project the future hydrological elements at a global scale, and we design an emergent constraint method. Okay, the emergent constraint method, maybe you can just understand it as a relation-based method. By using the emergent constraint, we can use the observation to constrain the climate model simulation. So it's a good way to reduce the projection uncertainty. And we find that by using our emergent constraint, we can improve the projection performance at a global scale. After projecting future hydrological regime, such as we have projected future precipitation extreme and the flooding events, then we can answer the question, does the host structure imply a potential upper bound for future extreme? We find that, okay, I will show you just a simple plot. This is the host structure during historical period under climate warming. The host structure will change to the green curve. So we find that along with an increasing peak point temperature, the host structure shows an upward shift, resulting in a significant intensification of hydrological extreme in the future. And this is just the projection in China. We find that with the change in host structure, the flooding risk in China will intensify by 10 to 30%. So let's go to the final conclusion. Precipitation and the storm runoff extreme show a host structure with temperature rising, atmospheric thermodynamic intensified precipitation extreme, while dynamic decline precipitation in hot environment. The thermodynamic component do not always contribute to precipitation intensification due to change in temperature lapse rate. And more importantly, the host structure does not imply potential bound for future extreme intensification. Thank you. Thank you.
Thank you, Jiabo. That was an impressive journey through a tempest of numbers and equations, and you navigated us brilliantly. Now shifting gears from floods to the crucial realm of risk management, we have Dr. Adrián Morales Torres as a partner and technical director of iPRESAS. He has over a decade dedicated experience in dam safety management. Let's not keep the anticipation building. Please welcome Dr. Morales.
Can you hear me, right?
We can hear you.
Okay, perfect.
And we see the presentation. Great.
So thank you, Julian, for the presentation and also for the invitation to participate in this really interesting event. Yeah, first of all, just to introduce myself, I'm a technical director of a company called iPRESAS. We are a spin-off company of the Polytechnical University of Valencia, and our main field of specialization is the risk assessment and risk analysis. So since we use risk assessment results to inform dam safety management and to inform dam owners on how to make decisions to reinforce the dam safety, we have been working lately in how to introduce also climate change. So my presentation will be divided in two parts. The first part, I will speak more about the risk assessment methodology for the ones that are not so familiarized with it, and then I will explain how we use it to inform decision making. And then in the second part, I will focus more on climate change and how we are using the risk assessment methodology to evaluate climate change and to make decisions for dam safety based on that. So first of all, when we speak about risk in the dam safety field, we are speaking always about the combination of two things: probability and consequences. In this case, probability of dam failure, which will be the main problem related with dam safety, and then the consequences that would be produced if the dam fails. That will be mainly social or economic, environmental, cultural. So we will, from the risk perspective, we should always work in using these two parts. The probability, which is more related on how the dam is and what are the hazards for that dam, and then the consequences, what will happen downstream if the dam fails. And you will see that in my presentation, I will be always speaking about these two parts. So when we do the risk assessment, in general, we follow this structure and we divide the risk assessment in two phases. The qualitative phase, that is the most important one, is the one that we work with the dam owners, with the people that know the dam, the people that is in charge of the dam, and we work together in identifying potential failure modes that could happen in that dam. And then the second phase, that is the quantitative one, that we build a risk model that we use to quantify failure probability, to quantify consequences, and finally to evaluate the risk and to inform decision making. So this is an example of the failure mode identification process. As I have said, during this process, we put together the dam owners, different experts, people that know the dam, and all together in a workshop of several days, usually 2-3 days per dam, we identify what failure modes could happen. We also classify that failure modes, and based on that, we also made some recommendations to avoid the failure modes and to analyze them. Then we build a quantitative risk model. A quantitative risk model is just a mathematical tool. In general, we use event trees, but also other mathematical tools can be used. But it's a way to combine, to analyze all the different possibilities, all the different failure modes that could lead to the dam failure. And then what is the probability? We can calculate the probability of each one of these failure modes, and then what will be the consequences that will be produced if these failure modes happen. And the main advantage and the strongest point of these quantitative risk models is that they are able to integrate all the info related with the dam safety. So in dam safety, we have floods, we have hydrological studies, so we introduce that data within the flood node, that we introduce the probability of having different floods and the magnitude of these floods. Then we have earthquakes, so we also introduce that in the loading part. Then we have hydromechanical assets, so we also introduce different cases considering the probability of not being able to operate off the gate because we have any kind of mechanical, electrical problem. We also have the operational rules, so we also analyze how we operate the gates and what will be the maximum water levels that will be reached in the reservoir for each one of the cases. Then we have the failure modes, where we analyze the system response, and we have the structural safety. So all the studies that we have on the structural behavior of the dam, the factor of safety, all that we can use it to estimate the probability of each one of the failure modes. Then also what we know until now on the dam behavior, what the monitoring says, what the inspection says, all that we will also use it to estimate the probability of the failure modes. And then we have also the consequences part, which is more related to the emergency management, emergency action plan, the coordination between the different institutions. So finally, we also have operational maintenance, which is related with the three parts, with the load, systems, costs, and consequences. And finally, all of that in different reports. So that's the main advantage of the quantitative risk model, is that it allows us to evaluate all the aspects, all the issues related with the dam safety, and to analyze what are the most important ones in each dam. Maybe in some dams, failure probability is led by the hydrological hazards, maybe in others it's because of earthquakes, in other ones it's because there is some kind of internal erosion. So we can understand in each dam what is the most critical point, or the consequences, the emergency management, the hydromechanical assets, and then make decisions changing that point or reducing the risk of that more critical point. So finally, when we use the quantitative risk model, we usually obtain a result like this one. This is what we call an FN graph, where in the y-axis we draw the failure probability of the dam, and then in the x-axis we draw the consequences. In this case, we have estimated the loss of life, and we draw this estimation of loss of life. So the good thing about this type of graph is that it combines the two parts of the risk that we have said, the probability and the consequences. So then points around here will be dams with higher risks because the combination of probability and consequences is higher. Points around here will be dams with lower risk because that combination of probability and consequences is lower. So then doing that, we can estimate the risk for a dam, and then we can also compare it with international tolerability recommendations, combining all the aspects that we have seen in the previous slide. So in this case, these are the Bureau of Reclamation tolerability recommendations, and we can see that in this case, these two dams would not be aligned with that recommendations. So finally, we can evaluate different type of risk reduction options. In this case, these are two dams in Argentina, and we were evaluating 5 different risk reduction options. And we can combine the risk results with the cost of each one of the measures that we want to analyze, and then to prioritize them, looking for the measures that allows us to reduce more the risk at a lower price. So then we will see what is the best way to lower the risk of the dam and to bring it aligned with the international recommendations. This is an example. This was an example only with 2 dams. We have applied this in several cases. We are also working now with the Spanish government to apply the methodology and the prioritization for more than 300, for all the main 300 public dams in Spain. And this is an example when we apply it to 27 dams. As you can see here, we have very different dams from very different typologies. And we can obtain this type of results. We say in this group of dams, for instance, they were planning to have to implement around 95 different risk reduction measures, structural and non-structural. The total budget of these 95 measures were more than 60 million euros. So prioritizing following the risk methodology and the risk assessment, we can see that only with 3 million euros of these 60 million euros, we can already reduce the risk in the portfolio more than 1 order of magnitude. And we can see that after implementing the first measures of the sequence after spending around 20 million euros, the residual risk that we achieve is, sorry, the reduction of the risk that we achieve is more residual. So that shows us how risk-informed decision making and how implementing measures following risk results can help us to be efficient in spending the money and in implementing first the measures that help us to reduce more the risk in our portfolio. So also we can get all other benefits when we apply risk methodology. For instance, this is the case that I was explaining in the ICOLD conference in Sweden. It's a case of a dam in Colombia where we use real results to define the gate operational rules and to be sure that with that operational rules, the dam owner can demonstrate that they are operating the rules in a way that they minimize total flood risk downstream. They also improve the dam safety, reducing the probability of overtopping, and then they are also accounting with climate change. Finally, reinforcing the legal protection in case of any kind of flooding and problems downstream. Because we estimate the consequences that will be produced for different probabilities, including failure and non-failure case, and we look for the best strategy to operate the case to minimize that. We can also define rehabilitation measures, optimize rehabilitation measures based on these results, looking for the best way to align the dam with the territoriality recommendations without spending too much money. So this will be, all the previous slides will be more focused on risk management, and this is how we use these results also to evaluate climate change. The thing is that climate change is related with several of the input data that we have defined for the risk model. It's related with it seems that climate change is producing a higher frequency of extreme flood events. It's also having an effect on the pool levels in the reservoir, because if we have less resources available in the future, then pool levels will be lower in the future, and that can have an impact also on dam safety. It can produce also changes in the social and economic areas downstream, so we can also have changes a long time due to the climate change in the downstream population and in the consequences downstream, and also degradation of the dam or other type of equipment. So what we do is we compute risk for the current scenario, and then we recompute risk considering the effect of climate change in the input data in the risk model. So we obtain this type of results where this is, for instance, a case that we estimated some years ago, where we have for the different climate change scenarios, we could estimate risk in the base case, in the case in 2019, and then for the different future scenarios, we could estimate how the risk in the dam was going to change. So we can see that in this case, the probability of failure was going to increase because it was expected to have higher flood events, and that was going to produce higher pool levels and an increase of the probability of failure for the overtopping and sliding failure modes. This is the damage a concrete gravity dam. And on the other hand, we also had a lower consequences because this dam is located in a rural area in Spain, so we expected that to have less population in the future in that area. So in this sense, we can evaluate not only the risk today, but also how we expect the risk to change in the future, considering the different climate change scenario and also considering other effects like forcing or population changes or other time effects. Then with these results, we can evaluate how this changes a long time, and we can obtain the risk reduction benefits today for the reduction strategy that we want to implement, but also what will be the benefits in the future, because we not only calculate the risk today, but we also consider different future scenarios. And we can compare these benefits, economic benefits and social benefits, with the cost that this measure has. So not only the cost of implementation, but also the type of cost, like maintenance cost a long time. So finally, we can do this comparison between the cost of each measure and the benefits of the reduction of each measure, and we can evaluate what is the most efficient measure to be implemented, considering the changes in the risk and considering climate change. So finally, we will obtain this type of results where we have the risk today, how we can reduce risk by following or by implementing the different risk reduction actions, and what will be the prioritization of these actions, and what will happen if I don't do anything. So then I can demonstrate why I'm doing that prioritization, why I'm implementing the measures in that way, and also for dam owners, it helps them to demonstrate why they are investing in dam safety and what will happen if they don't do that type of investment. Finally, to end my presentation, I wanted to show you a platform that we have developed to do that, that we introduce the risk of different dams or the different dams, the change of risk a long time considering climate change, and then we can prioritize and we can obtain this type of results. This is, for instance, 6 different dams in Spain, and this is the failure probability of the whole of the 6 dams together, but we can represent also the incremental social risk, for instance, and we can see how implementing the different risk reduction actions, we can reduce the risk. As expected, the first actions in the sequence are the ones that help me more to reduce the risk, and then how I distribute the different actions that I have planned for these 6 dams a long time. And also what will happen if I don't do anything. So I can see how here I can reduce risk more than 3 orders of magnitude, thanks to implementing this type of actions. And also I can see that also in this type of consequences failure probability graph, where I can see how implementing the different actions a long time will help me to bring the dams to the tolerable area. So yeah, that will be the end of my presentation, just to highlight the importance of considering also climate change when we are doing a risk assessment. Of course, there are uncertainties on climate change, and we can have different results depending on the climate scenario that we use, but these uncertainties should not prevent us to use that results and to use climate change in decision making. And the risk management framework, it's a very good framework to introduce the effect of climate change in the different parts of the dam safety and to help us with decision making considering long time scenarios. And that will be all. Thank you for your attention. And also, I will be available later if you have further questions, but also here you have my emails. If you want to write me any question, I will be very happy to answer you. So thank you.
Thank you, Adrián, for illuminating the intricacy of risk management. Remember, everyone, to keep those questions coming in the chat. We are here to address them at the end of the conclusion of our presentation. Now, direction the Caribbean, introducing Mr. Ronny ROSILLETTE, a distinguished hydraulic engineer. Since 2020, he's been steering the ship of the collective territorial, the Martinique, as the head of Irrigation Water Operational Office. Let's dive into the Caribbean water management with Mr. ROSILLETTE. Ronny, you can present.
Hi, everyone. Can you see my screen? Do you hear me?
See your screen. Yes.
Everything is okay? All right. So let's get started. As you said, I'm Ronny ROSILLETTE, and I'm working at the Irrigation Water Operational Office at the Martinique Territorial Authority. And thank you for giving me the opportunity to present that paper. So the evolution of territorial issues and uses linked to the Manza Dam in the Caribbean, Martinique. So first of all, where's Martinique? All right, it's in the Caribbean, but where it is exactly? It's a small Caribbean island right here, located between the island of Dominica in the north and the island of St. Lucia in the south. So it's a small island, it's a French region. Its size is about 1,000 square kilometers, so 100 kilometers long and 35 kilometers wide, so it's pretty small. And it has a population of 360,000 inhabitants. So there is, compared to its size, there is a high population density, even though the population is declining over the past 20 years. So Martinique is the Caribbean, all right? Caribbean is known for tourism, nice beaches, but it's also one of the most natural disasters region in the world. So Martinique is vulnerable to natural hazards such as earthquakes because it's close to a subduction fault, a hurricane. The island was hit 16 times over the last 60 years, tsunamis, flood events, and also volcanic eruption because there is an active volcano, the Mount Pelée, which erupted in 1902 and led to the losses of 30,000 lives. So when we look closer on the island, it can be divided in two main areas, the northern parts and the southern parts. So the northern part, it's mountainous, so it's mostly covered by tropical rainforest, and it's also the main sources for the island's river. There are around 171 rivers in this part of the island. And the annual rainfalls varies from 5,000 to 10,000 millimeters. While on the other side, the southern part is drier, and there are less rivers, and it receives less than 2,000 millimeters. So Martinique, regarding the context, so the island became an overseas French department in 1946. Before that, it was a French colony. And the shift led to multiple consequences, like a deep social and economic crisis, like social movements, migrations from rural areas to urban areas, emigration to mainland France, elevated poverty or high unemployment rates. So it happened in the 1960s. And in addition to that, repeated droughts in the 1970s, which happened during 8 years, from 1970 to 1977, especially in the Southeast region. And this led to a decline by 15% in the total agricultural production. So after that, it was decided to create a new hydraulic infrastructure project in order to develop the Southeast, to develop agriculture in the Southeast. So for economic development, to create that. So the first thing is to ensure water availability in this part of the island. So this is how they created the Southeast irrigated area in 1980. So the water is collected from the north in the Lézard River, and then moved to the south, here in the irrigated area in green, through a 30 kilometers water pipeline. Here. So the water is collected here, supplied here, and stored here in the Manza Dam. So how does it work? Let's talk about hydraulic processing. So the water is taken from the Lézard River in the north up to 1,000 liters per second through a water intake. Then it passes through a sand trap and then to a pumping station. So the water is lifted to a head reservoir, which is 40 meters higher. So here we are still in the north part of the island, to the Deuter head reservoir. And from there, the water flows down by gravity through the water supply. Here, from 20% to 25% of the water is directed to water treatment plants, so for drinking water purposes. And the other one is for agriculture. So there are two types of irrigation for agriculture. Direct irrigation, which happens during the rainy season, when the river flow in the Lézard River is higher, is increasing to meet all demands for agricultural purposes and drinking water purposes. And indirect irrigation, when the stream flow in the Lizard River is decreasing. So this is the water stored here in the reservoir, which is used to supply the irrigation network. So there are two types. Regarding the Southeast irrigated area, so it covers around 8,000 acres across 7 municipalities. There are about 500 customers, 150 kilometers of water network, 300 irrigation hydrants, and a larger dam, the Manza Dam, which is here. And about the water uses, in 1990s, it was split equally between banana crops, livestock farms, and vegetable crops, 1/3 each. And today, bananas will represent over 60% of the water uses. So this is a significant growth over the last 3 decades. And I have to say that bananas requires a large amount of water to grow. So it led to a significant increase in the water demand today on the irrigated area. Regarding the dam, so it was constructed in 1979. So it's a rock-filled embankment dam with a central clay core. The dam owner is Martinique Territorial Authority. So it's a dam owner and operator. And we receive a technical support from INRAE. So 365 meters long and 27 meters in height. Its fill volume is about 300,000 cubic meters. About its surface reservoir, it covers 200 acres and has a capacity of 8 million cubic meters. So in Martinique, in the Caribbean, there's a tropical climate with 2 distinct seasons. The dry seasons, we call carême, runs from February to end of June. And the rainy seasons, we call hivernage in French, runs from July to January. So the Manza reservoir management is seasonal, so rely on the seasons, and with a draining phase, which lasts for 6 months, followed by a filling phase. Regarding the hydrological regime, so we collected data over the last 60 years, from 1962 to 2020, and it's clearly showing that the Lizard River has a tropical stream flow variability with a dry cycles here from January to June, and the wet cycles here. So during the dry season, the stream flow can drop to 0.3 cubic meters per second during the low flow. And we noticed that on the southeast irrigated area, when the stream flow goes below 1 cubic meters per second, the water resource availability is limited for irrigation supply, but is available only for drinking water supply. So this graph shows the variations, the reservoir storage variation during a particularly wet year in 2012. So the red line is the maximum reservoir capacity, 8 million cubic meters. The yellow line is the real volume during that time. And the green and blue line are 2 inflow simulations based on the cumulative volume available from the Lizard River. And what we see is with the current inflow, 600 liters per second, it takes 8 months to fill up the reservoir. And with a higher inflow, 1,000 liters per second, it doesn't exist actually, it takes 1 month less, so 7 months to fill up the reservoir. So with those simulations, this is a minimum time to fill up the Manza reservoir. And this is the potential volume available to do it. Here is a reservoir storage variation during a drier wet season, a specific drier wet season which happened in 2011 from July to December. So what we see is even with a higher inflow simulation in green, we cannot fill up the reservoir to its full rates. We reach 56%. So in this case, it's clearly showing that there is a lack of significant resource available for irrigation supply on this island. So let's step back. Here are the variations, the variation of the last 12 years from 2009 to 2021. And I have to say that for the first time in the Southeast irrigated area, we faced 2 consecutive severe droughts. In 2019, the reservoir dropped to 13% here and 8% in 2020. And then it was followed by a drier wet season in 2021 here. So it was critical time. And on the other hand, it's becoming challenging to fill up the reservoir. We reached 71% at the end of the rainy season in 2019, 74% and 61%. And in 2022, we reached again 13% here during a short drought, and we've reached there 82% because we implement more water restriction measures, longer and more severe restriction measures in order to manage the reservoir and to reach that level, but it's not enough. So today, we notice that there is an increasing water demand. So the total irrigation supplied is close to the maximal reservoir capacity, and some years is over that reservoir capacity, as it was the case in 2012 and 2015. And upstream on the Lizard River, we're facing limitation about the inflow capacity and also the water intake efficiency, especially during the rainy days, because 600 liters per second is not enough today to fill up the reservoir in a minimum time. So as a consequence, we have to implement more water restriction, so they became more severe and longer. For instance, in 2022, water restriction happened 70% of the year to reach 82% of the filling reservoir. So regarding the effects of the climate change, numerical modeling was realized by the French Geological Survey, BRGM, and it's based on climate projection on how the effects will impact the Martinique water resources over the next century. And we're expecting warming temperatures with more evapotranspiration, especially in the southeast region, which is already drier. So there will be a higher seasons variation. So the wet season is going to be wetter and shorter, while the dry season is going to be longer and more intense. So we're expecting less than 50% precipitation during the dry season, and it's going to lead to an increase in the soil water deficit. We're expecting also a decrease of the flow rates of the Lizard River, which actually fills the reservoir, the Manza reservoir. And as I said previously, the availability of the water resource coming from the Lizard River is decreasing over the year. And all of that combined with an alteration of water quality due to soil erosion, sedimentation, and pollution load. So there will be a higher quantitative stress on the available water resource on the island over the next century. So in conclusion, Manza Dam, or on a larger scale, the Southeast irrigated area, have a crucial role in Martinique it represents 30% of the total water supply and 80% of the total irrigation supply on the island. So Martinique rely on it. But today there is a decreasing of the water supply combined with an increasing of the water demand due to rapid banana expansion. There are some solutions on the Lizard River from hydraulic modeling to increase the water supply, the water inflow, by increasing the pumping station capacity or optimizing the water intake efficiency in order to store that water during the flash flood events or during the rainy days. But today, what we notice is the reservoir storage capacity is limited when the dry season is followed by a dry wet season. And also the effects of the climate change are expecting to be worse. So as a Caribbean island, we have to be resilient and we have to implement adaptation strategies, such as a new irrigation master plan, which is currently in progress, and also a new hydroeconomic model. We have to make an assessment of the irrigation potential, like the reuse wastewater supply. We have to create also more outside reservoir storage and make a transition to crops diversification in order to increase our resilience to the next environmental changes. Voilà. Thank you for your attention.
Thank you, Ronny. Thank you, everyone, for all four of you for your presentation. Now we will get to the question. If those who ask question in the chat would like to read them aloud, so everyone can get the answer to. So, Niels, I will try to give you access to the microphone if you're still available.
Don't give access to Niels for the microphone. He will not stop speaking.
Okay. So, Niels, if you might be able to activate your microphone if you want to ask a question.
Yes, I take that critique as well. I'll keep it short. You already answered my question initially in the chat, so thank you for that. Thank you for the presentation to everyone. Yeah, but I guess to share it in plenum, my question was related to the fuse gates, whether they considered the kind of breaching wave that would occur. So both that kind of flood wave, but also with regard to what kind of possibilities are in other structures or other dams. I mean, this spillway shape, for example, might also be relevant to discuss, right? Whether it's capable of handling excess water, right? If there's risk of cavitation, you know, something like this. Is that a general consideration you would do, or is it site specific? So yeah, it's to you, Angelo.
Hi, Niels. Nice to see you again. Hope you're well. Okay, let's go one by one because you didn't make one question. You made the 3 or 4. So let's take one by one to answer as best as I can right now. The first question I remember because you also wrote, it's about after the tipping, if a wave is created. So during our analysis, during the design phase, first of all, the fuel gates are not tipping all at the same time. They are tipping one by one, or in sometimes it can be in series of 2 or 3s, depending on the design. But we always check the increase of the water to be around or less from 5 to 10%. So this is not a significant amount of increase in the release already released of the flood. So there is no extra wave created from that. So can we go to the second one? Cavitation, you said? Cavitation, what has to do with cavitation effect? Doesn't have to do with raising the reservoir level. The speed doesn't change from that.
No, I'm just mentioning with regard to this, let's say, this design or this method of raising the elevation on other spillways. So if the spillway shape is designed for a particular water level, you now raise the water level so that you're over the design head, which can induce subatmospheric pressure and cavitation. But it looked, from the images, it looked like the spillway was rather flat, so not so inclined. Just maybe more a general.
You mean, if I understand, correct me if I'm wrong, I understand that you say that the initial design of the spillway takes into account, you mean not cavitation into due to subpressure on the spillway structure, not on the chute. This is what you mean, right?
Yes.
Okay. So in this case, but in all the other cases, aeration and subpressors have also been studied for fuse gates in the lab for many years. And yes, the spillway shape with the fuse gate it's changing, but the change that is done is in this case and in most cases it's just like a normal labyrinth shape. Yes, of course, it's not the same as before when you have overflow from the top of the fuse gates. It's not the same as it is before, but it doesn't create subpressure issues on the bottom where you had the previous spillway structure.
Yeah, cool. Thank you.
And the third one?
That was it. But I could, if I may, if I not to follow as Andreas said that I would not stop speaking, but I have just one quick question to Ronny.
That was a joke. I took the liberty to make.
Now I'm delivering on
otherwise
your
I would not do it. Sorry?
I'm delivering on your joke now because I have one quick question for Ronny. And with regard to the irrigation and let's say the water demand surpassing the supply and this increase in water intensive crops. So does the government already regulate what kind of crops you're allowed to grow, or is that a plan?
This is not for me, I guess. This is for
Ronny, yes.
Okay.
Could you repeat, please? So
my question for Ronny was whether the government regulates what crops are allowed to be grown, or if that's in the plan. I'm sorry if my connection is poor, or I'm not sure.
Yeah, in Martinique there is banana crops is for exportation for the European market. So it's for economic development for the territory. So today there's an opportunity due to the European funds to expand it and to do this. So the problem is today banana farmers, they have a specific target to meet per year in order to feed the European markets, and they need water, a large amount of water. And this is only economic development. So this is an economic approach. But the problem is the water supply is decreasing while the demand is increasing. So today we need to, it's a political issue today. We need to develop our self-sufficiency about the food security. And for that, we have to have a new approach for the island. I don't know if I really answered the question.
Yes, you did. Thank you. Thank you to everyone.
Thanks.
Thank you, Niels, and thank you, Evangelos. Thank you, Ronny. Ronny, you're still sharing your screen. I think we would appreciate to see your face instead of your screen. We'll give the microphone to DB Assassi. DB Assassi, you should be able to open your microphone, and you're welcome if you wish. DB, are you still with us? Otherwise, I will read your question, which was about environment. Tell us more about the environmental issue occur with the rise of the water in the reservoir. Evangelo, if you can.
Yes, thanks, Julien. Let me find the question so I can read it. It was for the environmental. Okay. During the design phase of any dam, environmental impact studies are performed and issued, and in most of the cases, I think it's in all, but I cannot say all because I don't know the regulations in all around the world. The limitation, the impact study for the environmental impact study for any dam is performed with the maximum water level. In some cases, also with the dam crest level. This means that there is an area that limits where the water goes. It's never below the maximum water level, because this is the level that the water from the study is supposed to reach at some point. So this is the limit. There is a perimeter. This is how it's routed, and from this you go to analyze and find all the rest of the impact of the dam. So once this is done, so dam is constructed, changing the full supply level, which is something that the fuse gates do. They change the full supply level, which is below the maximum water level, doesn't impact this this environmental, the initial environmental impact of the dam, because it has been calculated for bigger, for a larger level.
Thank you, Evangelo. We have a question from Isaac. We give you access to the microphone and to the camera. You can speak up tell us your question. I think it was addressed to Dr. Yin. Isaac, can you activate your microphone? Otherwise, I will ask the question for you. So it was about, you say you would like to know if the project and studies presented here seeks to incorporate extreme weather events into dam structure, taking into account the physical construction of the structures and their surrounding, just as slopes, etc. In addition, the impact of phenomena such as El Niño and La Niña are measured. I think it's a question addressed to Dr. Yin Jiabo. If you can respond to this question. Jiabo, your microphone is off. Are you still able to activate it? Maybe not. If not, I will try to find the next question in the chat. Is there any seismic design and construction requirement specific for the fuse gate solution presented? Evangelos?
Yes, thanks again, Julian. Stability is checked and stability analysis is performed. As per specific requirements, fuse gates don't have specific requirements. They are freestanding elements. They are set on the spillway weir. They're not fixed. And the requirements, the dam requirements for the seism, specifically the dam requirements are also applied for the fuse gates. There's no something special. In particular, yes, fuse gates have been tested with the seism. Usually, what happens if there's a very large seism, they might move a little bit and have some leakage.
Thank you,
But it's the same requirements as the dam.
Right.
Thanks.
I hope Elias respond to your question. Jiabo, can you get back on the question we just asked about the? I will read it again. We'll try to find it back. Oh yeah. Do you seek to incorporate extreme weather event into dam structure, including such as El Niño, La Niña? Jiabo?
Hi. So could you repeat your question? I didn't find the question.
Okay. So it was a question from Isaac from Brazil. He would like to know if the project and study presented here seeks to incorporate extreme weather event into dam structures, taking into account the physical construction of the structure and the surroundings, such as slopes, etc. In addition, if the impact of phenomena such as El Niño, La Niña are measured or not.
Okay, thank you. I think this is a very interesting question, and the question also provides some insight idea for my future study. I think at the current stage of my research, because we have evaluate the risk of precipitation extreme and the flooding. So I think because under climate change, the flood events will also increase in a warming future. So I think if we need to design the dam structure and particularly the flood control standard, we should take the climate change into consideration. For example, by the late of 21st century, the flood events may intensify by about 10 to 30%. So if we need to keep the dam security, we should also take the land stationary risk of weather events into consideration. By using this, can we keep the dam security? Thank you. Thank you for the question.
Now we have a question for Dr. Morales. Can you tell us a little bit about the annual failure probability? Does the failure probability include all the failure scenarios? If so, based on what method do you evaluate the probability of each failure? And how do you combine them into one single value?
Yes, when we estimate failure probability, first we make that potential failure mode analysis workshop where we select the failure mode that we want to quantify, and then depending on the failure mode, we use different methodologies to estimate the probability. If they are more structural type of failure modes, we use structural numerical modeling. If they are more related with overtopping, we use the hydrological analysis. If they are more internal erosion, we use some references and tables. So for each type of failure scenario, we estimate the probability in a different way. And answering the question in short, yes, the results combine the annual failure probability of all the potential scenarios and their consequences.
Thank you, Adrián. I'm looking through the question, try to not miss any of them. Can you give us an example of the required action to minimize the risk consequences?
Yes, the good thing about risk models and about the risk management framework is that we can evaluate the effect of any kind of action related with dam safety, from structural actions like a dam rehabilitation of the drainage system, building a new spillway, any kind of structural action, and also any kind of non-structural actions like improving the monitoring system, improving the surveillance, implementing an emergency action plan, improving the way that we are maintaining the gates. So with the risk framework, we can evaluate the effect of each one of these actions in the risk results and then compare the cost of the actions with the effect that they have in the risk results. And in general, it's true that non-structural actions like emergency planning or monitoring are much more efficient in reducing risk than large rehabilitation measures. And we can check that and we can compute that with the risk analysis.
Thank you, Adrián. We have a question from Moussa Kabore, addressed to Dr. Yin and Dr. Morales. I think it's about the qualification of the data. How much are they certainty or uncertain? I don't know if Moussa Kabore can tell us more about his question. We'll try to activate his microphone. You should be able to switch on your microphone now and your camera. If you're still with us, you can ask your question about climate change model design and can they be classified in the certain or uncertain. I don't know if it's that ring a bell for you, Dr. Yin? No, we need, okay. I think we went through other questions. If that's all, I'm just checking. Feel free to add one if you see one that I missed. All right. So I think that's all for today. Yeah, we might have a closing speech from Mr. Yang.
Thank you, Julian. We have run out of time, but thank you, Julian, for your skillful navigating us through the informative presentations and discussions. The depth of knowledge shared by our excellent speakers is truly commendable. And the exchanges of ideas and insights also impressive as we near the end of this webinar. On behalf of ICOLD YPF, I would like to express our sincerest gratitude to the distinguished speakers for their invaluable contributions today. Your expertise is enlightening and will undoubtedly contribute to a more sustainable approach to water resource management. Also, I would like to extend our heartfelt appreciation to all attendees for your active participation, your engagement, and commitment to addressing the challenges of sustainable water resource management. Also truly commendable. I believe all of you have had a fruitful and inspiring meeting, and I hope you live with a renewed sense of purpose and deeper understanding of today's topic. Your participation strengthens the global network of young professionals in the dam and the hydropower industry, and it reaffirms our commitment to building a sustainable and resilient future. It is a passion, expertise, and dedication that will propel us towards a sustainable future and ensure the responsible development and management of these vital resources. If you have further questions about the presentations today, please feel free to contact us. We'll post the email addresses of the speakers and also ours to the ICOLD YPF LinkedIn group or somewhere you can reach, and hoping we have further exchanges after the meeting. Thank you once again, and that's all for today's meeting. Goodbye.
Thank you, everyone.
Goodbye. Bye.
Goodbye.
Thank you. Thank you, Ms. Nombre. Thank you.